In this course you will be learning about analog circuit design, that is now in this course we will concentrate on three aspects. One is how to design an analog circuit, how to design a analog circuit, and then the second aspect is we will also concentrate on the so called error budgeting. And then thirdly we will also concentrate on various techniques involved in analog circuits. So these three are very important in analog circuit design. Now if you look at it, look as an analog circuit design, what is that involved? It is basically putting transistors, op amps, resistors, capacitors and diodes and so on, various passive components and active components will put together and make a circuit. Now if you analog circuit design is is partly art, partly science actually, because you need lot of analytical thinking to put together these components in a working manner so that you will get the desired result. And this needs the designing analog circuit needs lot of analytical thinking and lot of experience as well. So you have to keep doing many circuits, then only it will come to you. Then the second aspect is when you are designing a circuit, for example you design a temperature controller circuit or temperature indicator circuit. When you are doing that, it is essential that you should know whether the desired accuracy is achieved in this circuit or not. For that we should understand what are the various errors involved and then how to compute the various errors, and then finally put together what is the total error that is expected in the circuit in the worst case scenario. Because in analog components what happens is that you have op amp, but then if I take say 741 op amp, that whatever error that you are getting depends upon the particular piece of 741 that you are using. For example, if they say offset voltage drift, offset voltage drift is not same for all the 741s. You know the maximum value, you know the minimum value. So while designing we have to consider what is the worst case error that is expected. So once you know how to compute these errors for a given analog circuit, that we call it as error budgeting. This we will concentrate very much in this circuit. Similarly, we also should know various techniques involved, like for example if I am measuring a capacitor, then just following the basic principle of capacitor measurement is not enough. We should know what are the various techniques already existing for the measurement of capacitance, so that there are no stray capacitance not involved and so on. That kind of things are must. So we also should know various techniques involved in designing analog circuit. So these three things will be concentrated in this course very much. And the problem in analog circuit design is that you don't have very many books concentrating on actual circuit design. You have books on error budgeting and techniques involved, also you don't have very many books. However, these two books what I am going to give here will help you somewhat in understanding this course. There is one is designing with one is designing with operational amplifiers and analog integrated circuits. This by Franco. Yes, this book is good for the error budgeting, and the second book actually is by Paul Horowitz and Winfield Hill. The topic is art of electronics. So these two books are good for you for reference, and the first book, the Franco, yes, it actually gives you a lot of information about error budgeting, and this art of electronics gives you a lot of information about circuit design techniques actually. So this is about this course. Now we will first see what is the background that you need to learn this course. So I will just start with transistor amplifiers, and then what is the issue involved in that, and from there how the op-amp had come in, and then we go ahead from there on how to design the circuit. Basically I will expect you to have some knowledge about basic working of the transistor, and then basic working of the operational amplifier, and then how to use resistors, capacitor and so on, and the basic Ohm's law. These are the background material that you have to have and you should have learned. Without that it is not possible to understand the course, but however I will repeat these things little bit in the beginning so that you will able to follow the course. Okay. Now let me start with transistor amplifiers, because we are all familiar with the transistor amplifiers in your undergraduate course. So however I will repeat this so that there is a continuity in this. So if you take the transistor amplifier, now the transistor amplifier circuit, if we look at it, it looks like this. You take, for example, I take NPN transistor, then if you look at the amplifier, that looks like this. You have a power supply here, and then you have one resistance connected at the ground side, then you have two biasing resistors, and that is connected to this one, and then to the input we connect the AC source. So you have the supply is connected here, essentially you have a DC source connected here. So you have a DC source connected here. So assume that this is around 15 volt supply. We have connected the positive to this, and then we name these resistors. We have RL, we have RE, this is R1, we name it R2. Then you have the capacitor C, and this is the signal source, AC source. Our aim is we want amplify this signal, and then amplified output supposed to appear here. This amplified output I will take it through a decoupling capacitor, and that is the load resistor. Across this you will get the output. So this capacitor I will call CL. Now this circuit is familiar, I hope, for most of you, because we have already done some basic course in this. Now my aim for picking up this circuit as a first example is that we have to understand what is the problem associated with this. From here on, how the analog electronics had grown to the present day status. Now, if you look at this circuit, basically this input signal is amplified and the amplified voltage appears here. Now, what is the basic philosophy involved in using the transistor? Essentially, we have to forward bias the base emitter junction and reverse bias the base collector junction. Now, if you take this voltage 15 volt, actually that is divided between R1 and R2, because R1 and R2 is acting as a voltage divider. For example, if I forget about this one, for example, I remove this and then I remove this. Now, this is nothing but a voltage divider. So, depending upon R1 value and R2 value, you will get a voltage at this point. Now, what I do is I will now redraw this. For example, if I have this is 10K and this is also 10K, then I will get half the voltage. For example, this I will get 7.5 here. So, I can select of course any values. I assume that I put R1, R2 are equal start with. So, I will get 7.5. Then I connect this 7.5 to this point. Once if I connect to the base, that means base is at 7.4, assume 7.5, assume that the base current is negligible. In that case, automatically this emitter will come to 6.9 volt. This is because we know that for any appreciable conduction, we need base emitter voltage difference of 0.6, and this is a very important assumption that we have to remember, and we will be using this at very many places. So, the base emitter voltage difference in the forward bias condition will always be around 0.6 if the transistor actually be in a useful working range. If the voltage is less than 0.6, then you will find very little current is flowing even in the collector, and normally you will never find above 0.7 volt across base emitter, because above 0.7 voltage is there, or if you apply above anything more than 0.7, you will find enormous current is flowing in the collector circuit. That is why we take this 0.6 volt as reference level in any transistor for the forward condition. So, this we will be using throughout this course. So, this is coming because the forward biasing of the base emitter, if you plot the base, this base emitter current, base emitter current versus VBE, if I take base emitter voltage, that actually goes exponentially like this. So, the 0.6 is somewhere here. Above 0.6 you see very high current. So, essentially we can assume that always if I give some voltage here and the emitter will be 0.6 volt less. That is why here I have given 7.5 and assumed 6.9. Once this is assumed, then if I know the resistance value, then I know this current, because this is 6.9, I know the resistance value. So, this current is known, and then we know that the collector current and emitter current are almost equal, because ideally speaking the emitter current is collector current plus base current. So, the this current consists of IB plus IC, that is equal to IE, the emitter current, but then IB is very small compared to IC. So, we normally take collector current is equal to emitter current. So, I know this, that means I know the collector current, I know the resistance value of this. So, I can find out what is the voltage across RL. So, voltage across RL is actually comes to be this resistance value into IC. So, once it means once if I know the base voltage, then immediately I can write what is the emitter voltage, then immediately I can find out what is the current through this resistance. Once I know the current through this resistance, I know the current through this, then I know the resistance value. So I know the voltage across this. If voltage across this is known, then immediately I can write what is the voltage across the collector, because this is 15 and if this voltage is 5, then I know that this voltage is 10. So that means once I know the base voltage, I can write what is the voltage at this point, what is the voltage at this point. This is a very important thing, because we have to know what is the voltage that you expect at different points, particularly at emitter and collector. So if I want to use this circuit for amplification, then I should know how much resistance I have to keep this, how much resistance I have to keep here, or other way around, what is the voltage I have to keep it here. In this example I just taken it 7.5. So what is the ideal voltage that I had to keep at the base? Now ideally speaking, I am looking at, I am taking the output voltage from the collector. So the output voltage it will be AC, that means the voltage will go up and then come down. If it is a sine wave, then the voltage will go up and come down. So if I want a equal swing, ideally keeping this at 7.5 is best. So I keep this at 7.5, then it can go up to 15 and also come down lower side. So we try to keep this in the normal case without any AC signal, we try to keep it at 7.5. So how to keep this at 7.5, and then also we have to decide what is the gain that we want. Assume we want gain of 10. If you want gain of 10, then this resistance RL and RE should have a ratio of 10, because you see whatever voltage I am giving here, for example I give a AC voltage through this capacitor, I apply the AC voltage through this capacitor to this point. Now at this point you will get the DC voltage plus this AC voltage, both are added together and coming. So if you take this one, so voltage at this point will be this AC plus whatever the DC voltage that is given by this R1 and R2. So this voltage will be amplified and then coming at this point. But we know whatever change that is happening here, that have to happen here as well, because this and this are differ only by 0.6. If it is say if it is at 7 volt, then this will comes to 6.4. If it is 8, then this comes to 7.4. So basically leaving that initial difference of 0.6, at any time whatever change that is happening here, that is happening here. That means if I give a signal, AC signal here, if that AC signal appears here, the same AC signal will be appearing across this resistance. So if the signal is 10 millivolt, then you will see that the 10 millivolt automatically comes across this resistance RE, and we know that this current is same as this current. So if the signal voltage is 10 millivolt, the 10 millivolt AC is appearing across this along with the DC, then automatically the AC, the 10 millivolt AC produces a varying current here, that also will produce a varying current here. So here also you will get a AC automatically. So the AC voltage will be more if the resistance is more, the AC voltage will be less if the resistance is less. So basically the gain is determined by the ratio between RL and RE. So the gain of the circuit is actually given by RL by RE. So if I need a gain 10, for example I need a gain 10, then I have to make sure this ratio is factor of 10. Now for example I can take this as 1K and I can take this as 10K, then I can expect gain of 10. Okay, you fix this one and then you fix this one. Now we have to fix this R1 and R2. Now if it is 1K, then if I want to keep this one at 7.5 volt, that is a midpoint of the power supply, because power supply is 15 volt, I want to keep this at 7.5. Then if this voltage is fixed, then automatically this voltage across this is fixed, that is 7.5. If the voltage across this is 7.5, then since the same current is flowing through this, voltage across this will be 0.75, because the voltage across this is 7.5, the ratio is 1:10, this current and this current are same, so automatically the voltage across this has to be 7.5, that is a DC voltage, 7.5 will be there. If this is at 7.5 volt, then this automatically is supposed to go to 0.6 extra, that is 0.75 plus 0.6, 1.35 volt, this will be 1.35 volt. So if I keep this one at 1.35, this will come to 0.75, this will come to 0.75, and then if this is 0.75, then the current of 0.75 milliampere is flowing. The same 0.75 milliampere goes through 10 volt, that will produce 7.5 volt difference across this. That will make this point sit at 7.5. So all that need to be done is I have to keep this at 1.35. That will make this fellow sit at 7.5, and then this fellow sit at 0.75. That is assuming there is no AC signal. Assuming there is no AC here, then I want bias this. I remove this. So this is 10K. I want to keep 7.5. Then I keep here 1.35. Now to keep 1.35, what is the values I had select for R1 and R2? Now originally we assumed that base current is negligible. We can continue to assume that, but actually we know this current is this voltage is 0.75, this 1K, so current of 0.75 milliampere is going, and then automatically we can know the base current, because this emitter current and base current differ by HFE times, that is beta times. If I take for this transistor beta as 100, then if this is 0.75 milliampere, so base current is 0.75 milliampere. So base current is current is equal to 0.75 milliampere. Sorry, actually emitter current is 0.75 milliampere. Emitter current is 0.75 milliampere. That means base current will be 0.75 milliampere by 100. Here we are taking 100 as beta of the transistor. So that will give you around 75 milliampere current at the base, because 75 microampere, that's coming as 100 actually. 75 will be 750 divided by 100, 7.5 microampere current. So this base current comes out to be 7.5 microampere. So this current is 0.75 milliampere. This turns out to be 7.5 microampere. So actually there is a small current through this. Now we select this current more than this 7.5 milliampere to make it, this current has no effect on this voltage division. I fix this current 10 times more than this. So I fix 75 microampere for this. So the essentially if I see this, now I need current through R1, R2, current through R1 and R2. R2 will be 75 microamps. That is, I have taken 10 times more than the base current. So I know the current through this, I know the voltage at this point is what is required is 1.35 volt. So 1.35 volt, and then I know the current through this, so I can select this resistance, then I can select this resistance as well. So this R1, R2 can be selected that way. Now once that is selected, then we can apply the voltage, because this is we kept this one at 1.35. Now I can apply the voltage here, AC voltage through this capacitor. This actually blocks this 1.35 volt from getting shorted. So this capacitor is required, but this AC goes through this, and that is applied across here, and then you will get whatever this. Suppose if I put 10 millivolt here, the same 10 millivolt, that is 7.5 plus this 10 millivolt comes here, and that produces AC variation across this, and the same variation is taking place here, and then you will get 10 times amplified voltage at this point. Now this type of amplifier is very popular, and all that you need to do is that you select these resistors correctly. That is, for example, we want 10 gain, I put a ratio of 1:10, then you get amplified by a factor of 10. And we also know that when the voltage increases here, for example, when the input voltage goes up like this, then this also will go up like at this point by equal amount. Suppose if this goes up by 10 millivolt, this also goes up by 10 millivolt, then the current increase will be 10 millivolt divided by 1K. That is the increase in current. Similarly, when the AC voltage goes down, this current also will decrease by the same amount. So here also the current increases by the same amount and then decreases by the same amount. That is, when the voltage is increasing at the base, this current is increasing. When the voltage decreasing, this current is decreasing. Then if you look at this point, then when the current is more, you have more voltage drop. So voltage at this point comes down, because voltage at this point is 15 volt minus voltage across this. So more voltage across this, it gives you less voltage at this point. That means when AC is voltage is rising, the current through this is rising, voltage at this point is decreasing. So that's what you get it like this. So this is what it looks at the input, and you get at the output the inverted voltage. That is, essentially you get the input is like this, then you get at the output 180-degree phase reversal waveform comes here, and of course this amplitude is 10 times more than this. Now this AC circuit working was good, and people are using this basically during the Second World War or even before that, predominantly for radios, amplifying the radio signals. Radio was the main thing at that time before Second World War. That radio usage was the main thing for electronics, and everything was centered around only radio. That is because at that time they need mainly this AC voltage to be amplified for radio use. But then when they tried to use this amplifier for DC application, then this amplifier started giving many problems. For example, if I try to see how to use this for DC amplification, then immediately we get into many problems. Like for example, if I have the same transistor amplifier, I want DC gain of 10, then what I do is I will put this resistance, then apply the voltage, then I know that I have to have a gain of 10, so I put this 1K and 10K, ratio of 10, then the gain comes 10. Then I have to bias this, because I want to keep this one at the midpoint 7.5, so that when the signal is applied, this will go up and down. So I want to keep 7.5, then I know that if I want to keep 7.5, then 7.5 volts drops would be here, then 0.75 volt drop here, and this has to be kept at 1.35. Then I can do that by selecting these resistors, this R1 and R2. Then if I apply DC, then I can put this and apply a DC voltage here. Now if this voltage, if I vary, then voltage at this point will vary, and voltage at this point will vary, and voltage at this point will vary. Then this DC voltage will get amplified, and then you will have more change than what change that you given at this base. So by looking at this voltage, I can say what is the voltage that is applied here. But then this looks fine from theoretical point of view. However, when they were using this, they found the voltage at this point was changing, even if the supply voltage was changing also. So if the supply voltage changes, for example, if it goes from 15 to 16, then you will find originally when there is no voltage was here, this was sitting at 7.5. Soon that when it goes to 16, then this voltage also will increase, then this voltage also will increase, then you will find this voltage is decreasing. So with supply also this voltage will be changing. Similarly, other serious problem is then when temperature changes, then this transistor which is kept in the ambient temperature, the temperature of this also changes. And when that happens, the base emitter voltage which was there, say at room temperature the base emitter voltage was 0.6 for a given collector current. The base emitter voltage also changes because the temperature coefficient of the base emitter is 2.2 minus 2.2 millivolt per degree C. That is, for every 1 degree temperature rise, the base emitter voltage decreases by 2.2 millivolt. That means even if this supply voltage is constant, even if this base voltage is constant, if for example the temperature at 25 degrees C, if the temperature is, if the base emitter voltage is 0.6 and if this is sitting at 1.35, this you will get it as 0.75. This is the condition at 25 degrees C. Then when temperature goes up say by 10 degree, then base emitter voltage will decrease by 22 millivolt, and that will make this voltage to go up by 22 millivolt. That means this will not be 0.75, this will be 0.772. 22 millivolt will decrease, and that will make this voltage to go up by 22 millivolt. That means the current in this will increase by, original current was 0.75 by 1K. Now the current had become 0.772 by 0.772 by 1K. So once this voltage increases, this current also increases, that also increases this current, then this voltage decreases. That means voltage at this point changes because of this voltage change and because of this base emitter voltage change. Now this is a serious problem because we are looking this point, voltage at this point, to reproduce what is happening here, but then voltage at this point is not dependable because the voltage at this point changes even if this changes or if the temperature changes. So you are in trouble because we are not sure whether change that occurred here is only due to this or not. So there are many issues, like they were trying to do various compensation techniques to remove this, but nevertheless the problem was if you want to amplify DC voltage, it is a problem. So people were struggling, and then mostly the applications were restricted to AC. So transistor was not very not thought that it's not a very convenient device to amplify DC. The same thing was there at that time with vacuum tubes as well. Even when they were using vacuum tubes, that amplifying a DC is a problem because this so-called change, or we call this is a drift. The drift at the voltage at this point due to temperature and the power supply is a major issue. So various attempts were made to solve this issue. Only when this issue was solved, then the operation amplifier came in, and then there once the operation amplifier came in, and then analog electronics started growing very rapidly, and as well the other digital as well as the power electronics also started growing very rapidly after this point only. And this is a very significant thing as far as electronics is concerned. If they have not solved this DC this problem, the DC drift problem, probably electronics wouldn't have grown to this extent even today. So that's why I had picked up this transistor amplifier first for AC amplification, and then I had shown what is the problem for DC amplification. So what was how did they solve this issue, that the drift problem, and that actually was the birth of operational amplifier. Now actually to see how the operational amplifier was born, we had to go back in a time scale little before. Just little before the World War. Actually the whole thing was started in 1941. In 1941 one gentleman named H. Schwarzschild Schwarzschild was the one who who patented one small circuit which actually opened up a new topic. Now, if you look at Schwarzschild's work, what is that he had done? Basically, what he had done was that basically um, he had taken the same transistor amplifier what we had discussed. He had taken 3 transistor amplifiers, that what we had shown there. You have one, then the second one, okay, then he had put one more, basically he had taken 3 transistor amplifiers, that what we discussed so far, that is then he was trying to applying the DC voltage, and then try to get the output here, and then this were all directly coupled here. Of course, he had put some biasing network here, and then I will not get into that right now. To explain this, what he had done is basically he had connected this essentially with this, then he had put in the input, for example, I connect a minus supply with respect to ground, then at this input I give. So, whatever voltage that is here is applied to this stage, then this voltage is applied to this stage. That is basically 3 stages of amplifiers. First stage, second stage, this output is given to the next fellow, then this output is given to this stage, and this output was given back to the first stage. It was given back to this stage. So, this is given some supply voltage. In fact, he had done it with vacuum tubes. I had shown you the transistor equivalent circuit. He had taken 3 sets of vacuum tubes, and one output of the first stage output was given to the second stage, and second stage output was given to the third stage, and third stage output was given back to the first stage. And this is a major development as far as electronics is concerned, and this only led to the development of operation amplifier. What he had done is that he had applied minus voltages here. For example, if this is not there, if this is not connected, then the minus voltage would have made the this actually to conduct almost nil. So you would have got high voltage here, the high voltage here would have put low voltage here, and then low voltage here would have produced a high voltage here, because once this is this voltage is high, automatically you get high voltage here, and that makes this one go low. And if this is low and this voltage comes low, this one goes high. Once this is high, and suppose if I connect this back here, if this is high, then automatically this will go high, and then this will come low, then that will make it high, and that will come low. But then where it will stabilize, because if this increases, if this voltage increases, that forces this fellow to come low. If this comes low, for example, if this is low, then this is high, low, and this comes high. That means if this is high, it forces this it works around, and then forces this to come to low. And in case if it goes low, again this will force this one to come high. Eventually what will happen is, if I stabilize the loop by putting capacitors and so on, you will eventually see this fellow which is getting contribution from this as well as from this, the 2 contributors, one from this feedback voltage, another from the applied voltage. This fellow trying to go close to 0, that is what happens, because when it close to 0, or when this is just about 0.6 or so, it conducts, and then it gets some voltage, so that this also gets some voltage amplified, and this also get amplified voltage that it comes from here. So eventually what he had shown was that if I apply 5 volt here, minus 5 volt, you will get back plus 5 volt here. So that if this resistance and this is are equal, you will get almost close to 0. So if I give minus 5, I will get plus 5. If I give minus 10, then I will get plus 10 here. So if these resistors, assuming this and this are equal, then if this is whatever voltage I am giving minus, I will get back as plus. So if I look at this one, he was using this as output. So if he gives minus 10, he will get plus 10 here. If he gives at this point minus 5, he will get plus 5. If he gives minus 1, he will get plus 1. That was his amplifier, and he called it as a summing amplifier. And this he had patented it, and then this circuit became very popular. Of course, at that time it was using the vacuum tubes. This was very popular, and then they want to use this during the Second World War in the army, because during the Second World War, that around 1941, British island was attacked by Germans using aircrafts every day night actually. So British want to develop a system by which if any aircraft enters into their space, they should hit them by using electronic system. So they had a radar network. So radar shows the incoming aircraft, but then they had also they had a gun to hit the aircrafts, but then there was no link between this radar and the gun, because if the spot appears in the radar indicating the incoming aircraft, and if there is a system which automatically connected to the gun, then the gun if automatically directed to the aircraft, and if the gun fires the aircraft automatically, then there will be a sure success. But at that time they had this anti-aircraft gun was there, radar was there, but then there was no electronics to link automatically these two, so that the aircraft can be hit. So in fact the British government asked the USA to develop this system, so that when aircraft is detected by the radar, it is automatically linked to the gun, and the gun automatically directs the get directed so that aircraft can be hit. So the so-called gun director, that is the gun director is nothing but the electronics that is to be developed. That work was given to the USA, and then it was actually given to MIT to develop this gun director. Now MIT looked at it, and they found there was, with the vacuum tubes at that time they had, it was very difficult to develop. Then this paper, the Swartz paper was there, and it looked like a promising one, because it is acting like a summing amplifier. You give this plus 10 and minus 10 are summed at this point. He called it, in fact Schwarzer called it as a summing amplifier. That means it gives a birth of analog computer. You can sum it two voltages, then the same way you can subtract, or you can multiply, divide, like all these functions if you perform, then you can develop a computer, and unless you have a computer you will not be able to develop a gun director. So essentially they want to develop analog computing machine, and with using that they want to hit these aircrafts. Now they found that they using this technique, this is summing amplifier, using this, if you have addition and subtraction, you can also perform multiplication and division and so on. So based on this principle, they have developed the gun director, basically using this, and then in fact they successfully connected the radar to the gun, and then the spot appears in the radar, automatically the gun director will direct the gun to the aircraft, and then the gun was fired, and it's supposed to go on to hit the aircraft. But then when they did this one, the success rate was almost 0. The reason was it was taking enormous time to calculate because the coupling between these two, to avoid oscillations, they had to put large value of capacitors at various places, and then in fact the gun director what MIT had developed was taking almost half an hour to spot the aircraft. To spot and direct the gun, it was taking half an hour. By that time the aircraft had vanished. So Germans had a field day. They were every day used to bomb this one, and then they were not able to develop a proper gun director. The problem was the circuit was very slow. Then this problem was understood, and then again MIT was on the job. Then MIT approached MIT wanted to develop the new improved version of this one. So they approached Columbia University to develop the so-called operation amplifier, which they can use successfully and hit that incoming aircrafts. So when they approached Columbia University, they had no one to develop there. Then it was they hired one person who was supposed to develop this operation amplifier, and that supposed to be used in the gun director. Now that I will tell that gentleman's name. He is still alive, even today he is alive, and he said he can develop this operation amplifier which will work in the gun director and which will be very fast in 30 days. And he developed that during that time, during the World War, the so-called operation amplifier that what we are seeing. He had developed that operation amplifier, and that was capable of doing addition, subtraction, the so-called multiplication, division, differentiation, integration, all that it can do. That we know that it's called operation amplifier today. That's the reason it is called as operation amplifier. And in fact, he had developed that operation amplifier in 30 days. And using he had developed 300 numbers of that, made 300 numbers of that, and he had given to MIT. Then MIT, supposed to be a computer experts, they hardwired these 300 operation amplifiers to make a gun director, and then in fact they got Bell Labs assistance in this. So put together, the Columbia University, MIT, and then Bell, all three put together, they made that first successful gun director. And that gun director was put in the next week itself in UK to detect the incoming to hit this incoming German aircrafts. So when it was put into the use, when German aircrafts had appeared on that day night, that radar had detected the incoming aircraft, and that information automatically went to the gun director. The gun director calculated the entire position of the aircraft, because the aircraft is already moving. So the gun director calculated the position of the aircraft, current position of the aircraft, and then also correctly given the at what direction the gun to be oriented and at what time it has to be fired, exactly calculated considering the moving aircraft, and then the gun was fired. That day it was hit the aircraft, it had hit the aircraft with 90% hit rate, success rate. That is, out of every 100 firing, 90 of them had hit the aircrafts, and aircrafts were down. In fact, next day no German aircraft was seen in the sky. Actually, Operation Amplifier was the hero of the Second World War. In fact, it was kept as a big secret. What is the how it was developed and so on. That too, it was developed using vacuum tubes, not with transistor. Because many of you may not be familiar today's transistor. Many of you may not be familiar with vacuum tubes. That's why I had taken the transistor equivalent of that and explained. So the story goes like that. The op-amp was developed essentially to hit these aircrafts. Now, what was this? How was that operation amplifier looked at that time? If you look at the operation amplifier, what they had developed during the Second World War, that is for the gun director what they developed was just with 3 vacuum tubes. If I draw the equivalent circuit of that in transistor version, that looks like this. You know, that 2 vacuum tubes, and then they connected this, then this was connected here, and this, and then the 3rd tube was used to in this mode. Equivalent of that, it was done with the vacuum tube, not this one, and this is the output here, this is the supply voltage. In fact, it used plus 15 minus 15 actually, not plus 50, plus 300 minus 300 volt. So I am showing it plus 15 and minus 15 for the transistor equivalent. This is output, and this is plus input of the op amp, this is the minus input of the op amp. This is the op amp equivalent that was developed during the Second World War. Now I am not telling that that person's name for particular to keep you guessing, because he is still alive, and he was just 21 years old when he had developed the world's first op amp that we are seeing on today's form. I will tell you in the next class what is his name. So this is the thing that he had developed, and if you see this one, you know, the wonderful thing about it is I can give AC or DC to amplify. For example, I give a DC voltage, the DC voltage will the voltage will be reproduced here, in this case as it is. If I want to amplify, I can do that. Now one significant thing about this is that this output voltage will not change, even if this voltage changes or even temperature changes. That is a major breakthrough, because now this operation amplifier, of course it was developed only for the Second World War, but then he had solved the main issue that, you know, if DC voltage applied, the DC voltage was changing at that time. That problem was solved. Now if I look at this point, this voltage is independent of this supply voltage as well as the temperature of these transistors. It only depends upon this. That means we can use this for amplifying the DC voltage. Of course, this also used can also be used for amplifying the AC, and also we can know that today the operation amplifier is used for integration, differentiation, multiplication, division, addition, subtraction, everything. All that you can do. So it looks like a great magic, because the problem what we had at that time, the Second World War, that the output voltage changing with respect to the supply and then the temperature change was solved. And this is a major breakthrough as far as electronics is concerned. Without that, probably electronics would have stopped with radios. Nothing else would have come. And also you have to realize that whole computer thing, the so-called computer that we are seeing, there are digital computers, but then the first computer came only in analog. And with that analog computer and with op amp, they had a 90% hit rate of the incoming aircraft, that even today they can't get it with even your Pentium 4 processor actually. Partly because that, you know, today's aircrafts are much more advanced and so on, but nevertheless the credit should go to this hero of this Second World War. And then from then on, analog electronics as well as digital electronics and power electronics, everything had grown, and this is the breaking point. But then the gentleman who is responsible for this to happen, who had developed this in just question of 30 days at the age of 22, is almost forgotten, and no one is remembering him. And the sad story is even it's not sad story, I won't tell. He had given an interview recently for Electronics Design magazine. He is alive, that's good. In fact, after the Second World War was over, he has started his own company to make various analog instruments, and he was supplying to US Army his instruments. Of course, he was supplying even as late as 2000. He was supplying. Recently, he had sold his company also. He was mainly supplying calibration instrument, so that the equipments are kept in a perfect shape. Probably electronics were not recognizing him enough. However, it is very important to understand how we able to design this, how we able to solve this drift problem that was hunting everyone at that time, and that will give us good insight into the world of analog electronics. And this is very important because we will be using this technique very much in our in this course at various places to design the electronic circuits. So you can go to the internet and see who is this gentleman who had developed this gun director during the Second World War. I will tell you that in the next class. So if you put this quickly, if you look at what we have done today, we have started our discussion with explaining what is a transistor amplifier, how the transistor amplifier works. Basically, the transistor, whatever signal that you are giving, that is amplified with 180-degree phase difference here, and I had shown you how to select the resistance, this resistance and this resistance, because if I want to gain 10, then I have to make sure this ratio is 10. For example, this 10K and 1K gives me gain of 10. Then I should select these two resistance. That two resistance selection depends upon what is the voltage that I have to keep it here. If I have to fix this voltage, then I have to fix this voltage, because I know if this and this differ by only 0.6. So to fix these resistors, first I fix voltage at this point. Voltage at this point invariably fixed at half the supply voltage. If it is 15, I will fix it at 7.5. Once this is fixed 7.5, then I know the current through this, I know the current through this, then I know the resistance value, then I will fix this voltage, that is 0.75, then this voltage is fixed. Once this voltage is fixed, then I will estimate the current here, then I will keep 10 times more current through this. So you know the voltage at this point, you know the current through this, then you can select R1, R2. So that is about the transistor amplifier. Then the main problem was that the voltage at this point is changing with respect to temperature and the supply voltage. To solve that problem only, then we went to the operation amplifier, that was this circuit. This circuit amplifies the DC voltage here, and this voltage is independent of supply voltage and the temperature. How this happened, that we will see in the next class.